All particles are described by what we call a wave function. Every possible measurement we can make on a particle is described by what we call a quantum operator. A quantum operator is a mathematical operation on the wave function that produces another function. Each type of measurement is associated with its own unique mathematical operation. When a quantum operator is applied, the new function that results typically has a different shape than the original wave function. But in certain special cases, the new function has the exact same shape as the original function, except for the fact that its amplitude has been scaled up or down by the exact same number everywhere. The amount by which the wave function's amplitude has been scaled is exactly equal to the value we end up observing for the measurement in question. Suppose that the measurement we are interested in is the particle's position along the x-axis. The quantum operator associated with the position measurement is to multiply the wave function at each point in space by the coordinate along the x-axis. Because each point has a different value for its x-coordinate, every point along the wave function is multiplied by a different amount. There is only one way the entire wave function can be scaled by the same constant amount everywhere when this operator is applied. This is if the original wave function is 0 at all points in space except 1. If the wave function is 0 at all points except 1, then when we apply the operator, it looks as if the wave function has been multiplied by the same number everywhere. The number which it is multiplied by is the value along the x-axis where the amplitude is not 0. And hence, it is this value that ends up being our observation for the position. Every possible wave function in existence can be thought of as a combination of an infinite number of functions that are each 0 at all points except 1. If this function is multiplied by the real number 3, the amplitude changes as shown. If the function is then multiplied by the imaginary number I, the function is rotated by 90 degrees as shown. On the other hand, if the function is multiplied by negative I, the function rotates by 90 degrees in the other direction. Suppose we have this infinite combination of functions. Suppose we multiply each of our original functions by a different constant. Each of these constants is a different complex number. By choosing the right set of constants, we can transform our original set of functions into any possible final waveform. Note, unlike what is shown here, each of these original wave functions must have an amplitude that approaches infinity at the one place where they are not zero. And we multiply each of them by a constant to make them smaller, not larger. However, infinite amplitudes are not possible to animate. When we observe the position, we say that the wave function collapses to one of the original functions. After the wave function collapses to one of the original functions, we obtain the measurement associated with that particular original function. The probability that the wave function will collapse to each of the original functions is given by the squares of the amplitudes of each of the corresponding constants. The probability that the wave function will collapse to each of the original functions is given by the squares of the amplitudes of each of the corresponding constants. In the case of this sequence, the squares of the amplitudes of each of these constants represent the square of the amplitude of the total wave function at each of the positions. Therefore, the square of the amplitude of the total wave function at each location determines the probability of observing the particle at that position. The principles discussed here for measuring position can be generalized to every type of quantum measurement. Each possible type of measurement has its own unique mathematical formula for its quantum operator. Each quantum operator has its own set of wave functions that just end up being scaled up or down when this specific operator is applied. Each of the wave functions in this set is scaled by a different amount when the quantum operator is applied. The amount by which it is scaled represents the value of our observation for this measurement. Each quantum operator has its own set of wave functions that just end up being scaled up or down when this specific operator is applied. Each of the wave functions in this set is scaled by a different amount when the quantum operator is applied. The amount by which it is scaled represents the value of our observation for this measurement. If the particle is described by one of the wave functions that just end up being scaled up or down when this operator is applied, then the value for our measurement is known with 100% certainty. If the particle is described by a wave function that is not in this set of wave functions, then we can write the wave function as a combination of the wave functions that are in this set. When we perform the observation, we say that the wave function collapses to one of the original functions in this set. We then obtain the measurement associated with that particular original function. Before we perform the observation, each of the original functions is multiplied by a constant and added together. The square of the amplitudes of each constant determines the probability that the wave function will collapse to that original function. In this example, we're measuring the particle's momentum in the x direction. The quantum operator associated with this measurement is the equation shown. Let us analyze each part of this equation one by one. This part of the equation is the partial derivative of the wave function with respect to x. That is, if the distance in the x direction changes by a small amount, then this part of the equation indicates how much the wave function will change. At each point, this change is a complex number, which can be represented with a vector as shown. This part of the equation consists of multiplying by Planck's constant divided by 2 pi. This just ends up multiplying the amplitudes of all our vectors by the same constant amount. This part of the equation is multiplying by negative I. Multiplying by negative I rotates all our vectors by 90 degrees as shown. Therefore, the new function described by these vectors has the exact same shape as the original wave function, except that its amplitude has been scaled by the exact same number everywhere. Therefore, the new function described by these vectors has the exact same shape as the original wave function, except that its amplitude has been scaled by the exact same number everywhere. When the quantum operator for momentum is applied, the wave functions that are just scaled by the same number everywhere are wave functions that look like this spiral. Suppose that the spiral has a shorter wavelength. In this case, the partial derivative of the wave function with respect to x is larger. Therefore, when we apply the quantum operator for momentum to a wave function with a shorter wavelength, the observed momentum is higher. Now suppose that we want to measure a particle's energy. The quantum operator associated with this measurement is the equation shown. Let us analyze each part of this equation one by one. This part of the equation is proportional to the partial derivative of the wave function with respect to time. That is, if the time changes by a small amount, then this part of the equation indicates how much the wave function will change. This change is a complex number, which can be represented with vectors as shown. If we multiply these vectors by the imaginary number I, all our vectors are rotated by 90 degrees. Therefore, the new wave function described by these vectors has the exact same shape as the original wave function, except that its amplitude has been scaled by the exact same number everywhere. When the quantum operator for energy is applied, wave functions like this one are just scaled by the same number everywhere. Now suppose we have a wave function that is rotating more quickly. In this case, the partial derivative with respect to time is larger. Hence, the resultant function is scaled by a larger amount. This means that when we apply the quantum operator for energy to this wave function that is rotating more quickly, the observed energy is higher. If many wave functions with different energy levels are added together, then the result may look as shown. If we try to measure the energy, this wave function will collapse to a wave function such as the one of the two we just saw. Much more information about quantum mechanics is available in the other videos on this channel. Please subscribe for notifications when new videos are ready.